SwayamPrabha. Digital India. Educated India.
Hello and welcome to the 12th lecture of the machining science course. Now, let me remind you what we were discussing is the practical machining operations, and the idea of discussing the practical machining operations is to show you that in different operations like turning, shaping, planing, drilling and milling, the tools used are different and the process is different. Although the turning, shaping and planing, as we said, that this is very similar because the tool used is similar, although the force distribution and the forces, direction of the forces is different. Now, in case of drilling, for example, we said that here it is different than what we have discussed in case of turning or shaping, because the thrust and the torque both, or the force that is both given on the given to the tool, which is the drill. If you see this diagram, here the torque is given here and this is the force, which is the thrust F, both are given to the tool, which is the drill here. Now, if you take a cross section AA, we said that it could be visible like this. So, here we have the tool with the rake face, and this defines the inclination of the rake face of the tool. So, in this case the tool is the drill. So, therefore, the drill has the two teeth, and we said that the feed is distributed to both of them, and therefore, the movement of the tool towards the workpiece, that is penetration of the tool, by one rotation of the drill will be defined as the feed, and this distance between this point and this point is given by F by 2, because this is the total feed is F and it is distributed by both of these teeth. Now, the angle from this tooth to this is given by the tool, this is point angle as we said. So, let us take beta as the point, half of the point angle, and in this case we said that the T1, which is like in case of turning, this is the distance, and this T1 is F by 2 into sine of beta, since F by 2 is here. Now, W, which is the width of cut, and we said that the width of cut is given in here, that is the width, how much width we are removing, and this is given by d by 2 divided by sine of the beta. Beta is once again this is the point angle by 2. The thrust force will be directed from this teeth towards the center of the drill, and this will be perpendicular to the teeth, all right, and the FC will be, FC will not be visible in this view, FC will be visible in this view, the top view. Okay. And this will be resisting the torque which is applied to the tool, that is to the drill, and the thrust is given by 2 into Ft, 2 of this Ft into the sine beta, and the torque is given by Fc into the d by 2. We are assuming that this is the half of the diameter, let us say it's acting at the half of the diameter, and the total distance between these two will be half of the diameter of the drill or diameter of the hole, as I said. So, I also like to remind you the diameter of the hole becomes little higher, bigger than the diameter of the drill because of the vibration during the drilling process. Power is given by UC into MRR, which is the same as U0 into, or UC is U0 into T1 to the power minus 0.4. This remains same as in case of turning, shaping, planing. So, the material removal rate is different than in case of turning. So, here the feed velocity is given as n by 60 into F, okay, and the area is pi d square by 4, since it is a hole. So, pi d square by 4 will be the area of the machining zone, which is the hole, and it is given in millimeter cube per minute. Now, in case of practical machining operations of slab milling, it is little different than the other processes, because here in case of drill we had the 2 teeth, in case of single point cutting tool we had 1 tooth, and in case of milling it is more than 2, it is multiple. So, the basic difference is that here therefore, the feed which is given, this is feed per tooth. Okay. So, per tooth the feed given is F, and this is equal to the Vf divided by n into z, and the Vf is the feed velocity as given shown in here. This is the feed velocity, and n and z, n is the RPM of the milling cutter. Okay. Here it is written, and the z is the number of teeth in the milling cutter. This is the feed velocity and this is the feed per tooth. Now, suppose you take this line, look at the line diagram, and this is one of the teeth of the milling cutter, all right. And in this case, this much is the chip which is removed by one tooth. When the milling cutter is rotating at an RPM of n and the feed velocity is given as the Vf. This is the depth of cut, this much material has been removed. D by 2 is the radius of the milling cutter, diameter of the milling cutter is D, and this defines the T1 maximum. Here T1 maximum is important because if you look at the chip, let us say this is one chip we have taken removed by one tooth of the milling cutter. So, here the T1 goes from minimum, which is 0, to maximum, all right. So, therefore, we take the T1 maximum, and this is the diagram which clarifies how the T1 maximum can be taken. This is the center of the milling cutter, and if you join this along this point, extend it. So, this is the distance which is considered to be the T1 maximum. This is the uncut maximum uncut thickness. Now, this is the radius of the milling cutter, D by 2, this is the same, small d is the depth of cut. Now, the T1 maximum can be assumed to be F into sine of beta, and the beta is the small angle that has been shown in here. Now, this is because we can assume this to be a line, okay, this chord, and from this triangle you can find out the T1 maximum is equal to F into sine of beta, sine of this angle. Now, here in milling process, the average value of the uncut thickness is used, which is T1 average, which normally taken as the half of the T1 maximum. Okay. Now, this T1 maximum is therefore given as the F sin beta, and the cos of this beta, cos of this angle is equal to this arm, that is r minus d, r is the radius here, minus d. So, this is the one, and then this is divided by this, which is r. Now, this value can be written as 1 minus d by r. So, therefore, the sin beta can be written as root over 1 minus cos square beta, cos beta is 1 minus d by r. So, we are getting root over 2 d by r, which is sin beta. Now, therefore, we say that the T1 maximum, which is given by f into sin beta, this is equal to f into, sorry, f is given by this. So, f into the 2 d by r. Okay. So, this is the T1 maximum value that we can express as. Now, you can see that here this is the difference between the milling operation and the turning operation, for example, or the shaping operation. Power is given in the same way. This is the product of specific energy and the material removal rate. Specific energy again is the same as in other cases, that is the energy spent to remove one unit volume of material, and UC can be given as U0 into T1 to the power minus 4. T1 here is the uncut thickness, all right. This is the T1 which has been shown here. Well, I mean T1 that you can find out from here, all right. Now, T1 average is shown here. This is T1 average which is taken, and this T1 average taken as T1 half of the T1 maximum. This can be written as U0 half of T1 maximum to the power 0.4. Okay. So, this is the difference between the turning and the milling process, because here the T1 varies from 0 to maximum as I said. So, therefore, the half of the T1 maximum taken as the T1 average as it is shown here. So, therefore, in this formula of UC equal to U0 T1 to the power minus 4, this T1 we take as a T1 average, which is half of the T1 maximum. Now, the U0 once again I will remind you that this is called the specific energy coefficient or the specific energy constant, and it can be defined as the specific energy required to remove 1 millimeter of the T1. T1 is the uncut thickness. So, here in this case will be average uncut thickness. Material removal rate is the same, that is the area into the velocity. This is the B into D is the area, and the velocity is the Vf, which is the feed velocity as shown here. So, the concept in all these things are remaining the same, that is product of the UC and the MRR gives us the power, product of the area and the velocity gives us the MRR, all right. Okay. Now, in the next topic we will be discussing the forces in machining. Now, the idea of discussing this is to show you that forces in different kind of processes like turning, shaping, drilling and milling, they are very different, and these forces are shown here once again. Although I have shown it to you when we were discussing the practical machining operations. For example, it is for turning, and forces of turning are the, as we said, that is this is the radial force, thrust force, feed force and the cutting force, although the thrust force is the summation of the feed force and the radial force. Now, in case of shaping, it is once again repeated, that is the Fc is here, Fn, Ft and Fr. In case of drilling, it is the N torque and the thrust is the F, and in case of milling, it is the radial or the total tangential force, which is the Fc, and the thrust force which is directed towards the center of the milling cutter. Now, here these are the forces for all the different operations, and as you can see that they are different. Now, how to measure these forces? That becomes a problem, because if you can measure by an instrument the forces in turning, that instrument cannot be used for measuring the forces in shaping, for example, or for measuring the forces in drilling or milling, because the forces are different. Forces, locations and the directions, they are different. So, let us discuss the measurement of cutting forces. The easiest way of defining is the axially loaded member. Suppose this is an axially loaded member, meaning that here this workpiece is given a force which is F, and this is axially located. So, how to measure this force? Now, gauges 1 and 4, these are the gauges. Normally, the gauges are used as the strain gauges, and these days in the dynamometers, as you know, the dynamometer measures the cutting force. In dynamometers, we also use the piezoelectric components or the elements. I will discuss little later what are those components and the strain gauges. Now, these strain gauges, let us say, or piezoelectric elements 1 and 4, they will measure axial strain, and the circumferential strain caused by the Poisson's effect will be measured by the gauges 2 and 3. So, if you can see that if when the F is applied, the axial strain, it will be affected, it will be taken by the or sensed by the 1 and 4 gauges, and 2 and 3 they will not be able to sense the axial strain that is happening in this part, in this component. Okay. The 2 and 3, the way they are located, this is perpendicular to 1 and 4, they will sense the circumferential strain which is caused by the Poisson's effect. Okay. So, the strain in the gauges will be then E1, E4, this will be F divided by A into E. F is the force, A is the area and E is the Young's modulus of the material of this component. And E2 and the E3, since they will sense the circumferential strain, this will be equal to minus F Poisson's ratio divided by A into E. Now, this is the simplest element, that is a cylindrical job, and this is a force axial load has been applied and this is the strains that you are getting. So, as you know that these strain gauges are arranged in a particular way, okay, and this is called the Wheatstone bridge. This bridge is the configuration of this bridge is shown here. It has an ammeter here and with the battery the power sensors. These are the sensors 1 and 4, as you can see that they are actually located opposite to each other. And this is because that when suppose apart from F, if any axial, if any load occurs perpendicular to F, in that case an opposite load, opposite action will be on the 4, all right. So, they will mutually nullify. So, that is why they are actually placed opposite to each other. Now, with this arrangement of gauges, the bridge output will be insensitive to any loading other than F, meaning that 1 and 4 will be measuring only the axial strain or the axial force, and it will not be able to sense 2 and 3, that is the circumferential strain. Suppose a bending load causes an additional strain in gauge 1, as I was telling you, then the gauge 4 will then have an equal and opposite strain and the effect will cancel out in the bridge, since gauges 1 and 4 are in opposite arms symmetrically placed. So, therefore, they are actually placed opposite to each other, once again I am repeating, and they are symmetrically placed. Now, let us see what is a strain gauge. Probably you many of you must have seen that. A strain gauge is something where the very thin wire is placed on a very thin paper like this, okay, and these are the two nodes. So, this is a thin paper here, this one very thin paper, and this is a thin wire. Okay. So, this will be rigidly pasted on the material, on the workpiece, and when the workpiece will be deformed, for example, in this case it is the axial load given. So, there will be an axial strain. So, when this will be deformed, then along with that these wires will be deformed, and when a particular voltage is passed through this. So, this voltage will be now according to Ohm's law will be changed, because this wire has been deformed. So, this is the principle which is used in the case of the strain gauges. Now, this deformation of the wire, because of the strain happening or because of the deformation which is taking place, the voltage which is passed here will also be changed, and that changed voltage will be proportional to the deformation that is taking place. By that we can actually measure the strain. So, therefore, we are saying that E1 in E4, E1 and E4 here, they will be equal to F divided by A by E, and with Poisson's ratio it will be minus opposite Poisson's ratio into the strain that has been occurred in the E1 and E4 node. Okay. Now, let us see the more complicated version of the strain gauges and the measurement. For example, it is a cantilever beam, all right. If it is a cantilever beam, then normally the load that can be measured or that can be sensed, it normally is sensed through the moment, because if the point of application of the load is known, that this distance, then the load into this distance will be moment. So, if you can measure the moment from there, knowing the distance from the application of the load, we can find out what is the force. So, this is the principle by which the forces are measured in the cantilever beam. Okay. So, let us take an example. Suppose this is the cantilever beam, okay, and in this cantilever beam there are two forces acting. One is the Fq, which is the thrust force, and one is the Fp, which is perpendicular to that. All right. So, there are two perpendicular to each other forces, Fq and Fp, and if you see in this section, you can see the Fq, the position or the moment of the point of action of the Fq and the Fp. Now, here we have the strain gauges. There are 4 strain gauges, 1, 2, 3, 4 on this side, 1, 2, 3 and 4 in this section you can see, and on the 90 degree there will be 4 more, 1 prime, 2 prime, 3 prime and 4 prime. So, if this is the distance as b and this is the distance as h, okay, then we can actually form 2 Wheatstone bridges, one comprising of 1, 2, 3 and 4, that is 1, 2, 3 and 4, okay, and the second Wheatstone bridge comprising of 1 prime, 2 prime, 3 prime and 4 prime. So, when the Fq will be acting on the cantilever beam, as you can see from here, the 1, 2, 3 and 4, these sensors will be sensing this, whereas 1 prime, 2 prime, 3 prime and 4 prime, they will be insensitive to this, insensitive to the thrust force Fq. So, therefore, Fq is measured by gauges 1, 2, 3, 4, 1, 2, 3, 4 and Fp, which is perpendicular to Fq, this is measured by gauges 1 prime, 2 prime, 3 prime and 4 prime. Okay. Now, E prime, E1, E2, E3 and E4 values will be given by 6 FQL divided by EBI square. Where from it is coming? In general, we know that the strain is equal to stress divided by Young's modulus. Now, the stress, normal stress, this can be found out by 6 m is the moment divided by b into h square. This is the formula taken from the solid mechanics. Okay. Now, the m is moment, which is the force applied here into the length F into L. All right. So, 6 into F into L divided by b h square, this will be the normal stress. So, therefore, the strain that we are getting will be 6 F L divided by E B into h square in general. So, now if we are measuring the E1, E2, E3 and F4, since they will sense the Fq, so therefore, this F will be Fq here. So, 6 FQL is the length and EB into h square. So, B and H will be in this. Now, E prime, E1 prime, E2 prime, E3 prime and E4 prime, which are these sensors, they will measure, as we said, the perpendicular to Fq, which is Fp. So, here in this case, in the general formula, we are putting in the place of F, Fp, because these are the sensors which are measuring, that is 1 prime, 2 prime, 3 prime and 4 prime, which are sensing the force Fp. And only thing is here it will be E into Hb square, because it is in the other side. All right. So, this is the principle which is used in case of finding out the strain or measuring the force through the strain of cantilever beam. You understand that if strain you have measured, okay, you know the L, B and H, you can find out the Fq. Okay. So, this is how indirectly you can find out the forces by measuring the strain. Now, let us see how it is done in case of a ring type dynamometer or ring type element. So, rings provide a high ratio of sensitivity to stiffness and at the same time have adequate stability against buckling. So, these are the elements which are also used to measure forces. Okay. Now, for example, if we have a ring like this structure and the side view is here, So, it has been seen that these are when they are subjected to the forces like F q and F p as shown here, it has been seen that the nodes where the maximum the strain is occurring, that would be at an angle of 90 degree and at an angle of 39.6 degree. This has been measured, or this has been found out by the photoelastic experiments in the for the element. So, if we have the sensors along the 90 degree angle, that is 1, 2, 3, 4, and at an angle of 39.6, which is 1 prime, 2 prime, 3 prime and 4 prime, okay, 3 prime and 4 prime. In that case, this 1, 2, 3 and 4, it will sense the F q, and 1 prime, 2 prime, 3 prime and 4 prime will sense the F p force. Okay. Now, for example, under the load of the action of the F q, the deformation of the ring will be like this, ring will be deformed like this, and under the action of the F p, the deformation of the ring will be like this. So, as you can see that these axes, that is C C, B A, B B and B prime, B prime, they are actually getting deformed. All right. Now, when the ring is subjected to normal force is the F q, inside of the ring will be subjected to an opposite state of strain from the outside. Hence, 4 active strain gauges can be located at 1, 2, 3, 4. So, this is the justification why the 1, 2, 3, 4 are positioned or located in the way it is shown here. That is, once again I am repeating that when the ring is subjected to normal force, inside of the ring will be subjected to an opposite state of strain. You can see from here, you can imagine from here that if it is deformed in this way, if it is going in one direction, inside that it will be in other direction. So, therefore, these are the 4 sensors or 4 strain gauges which are placed here. Similarly, in 1 prime, 2 prime, 3 prime and 4 prime, they are placed at an angle of 39.6 degree, because in a ring structure, photoelastic experiment shows that the maximum strains occur at that node, which are located at that 39.4 degree. Now, E90, it has been seen that the E90 at this 1, 2, 3, 4, this value will be plus minus 1.09, this is the coefficient, and F q, because it will be sensing the F q, R is the inside radius, okay, this is this radius, inside means this dotted line what we have shown here, what has been shown here, from the center up to the dotted line, it is the R. Okay. And E is the Young's modulus of the material of this structure, B is the width here as shown, and T is the thickness of this wall, thickness of this structure. So, at 90 degree, which will be actually measuring this, we have the Wheatstone bridge like this, consisting of 1, 2, 3, 4 sensors, and this Wheatstone bridge will give you the value which is here, okay, which will depend on the F q, R, E, B and T square. This is the thin ring elastic theory, from here it is taken, and at 39.6, where the maximum strain will be occurring, at this node it will be plus minus 2.31 F p R divided by E, B and T square. So, just notice here that at 39.6 it will be sensing these sensors, that is 1 prime, 2 prime, 3 prime and 4 prime, it will be sensing the force F p. So, therefore, here it is F p, and along the 90 degree 1, 2, 3, 4, these sensors will be sensing F q, which is the thrust force or normal force, and therefore, at 90 degree it is F q into R divided by E, B and T square. So, this is the principle by which the forces can be measured by using different kind of structures, be it a cantilever beam or a ring dynamometer or ring structure. Okay. So, here the strains are measured from the Wheatstone bridge, and from knowing the value of the R, knowing the value of the Young's modulus of the material, knowing the value of the B and the T, which are the physical parameters, we can actually find out the value of the FQ or the FP. All right. Now, here what happens, only disadvantage of the ring type structures are that it will tend to roll at when the FP is applied, as it is shown here. For example, see, now from here you can see that when the FP is applied, okay, how this is the FP, okay, how it is getting, all right. So, it is trying to roll. So, this is the disadvantage that the ring types structures have, but otherwise rings provide a high ratio of sensitivity to stiffness, as I said, and at the same time have adequate stability against the buckling. So, because of these properties, the ring type structures are used for measuring the forces in practice, that we will discuss in our next lecture. Thank you for your attention.